Swayam Prabha. Digital India. Educated India.
Welcome to Module 54. We shall continue the study of separation axioms, this time concentrating on checking whether they are productive. So the very first theorem here is that regularity is productive. Okay, so this is stated as the product xj of is regular if and only if each factor x little j is regular. Just as in the case of freshness, because regularity is hereditary, if xj is regular, okay, if x capital J is regular, then each xj is regular. Why? Because you can always think of each coordinate space as a subspace, each factor space as a subspace of the coordinate space, right? X cross y is contained inside, x cross singleton y goes inside x cross capital Y. So that is a subspace. X can be identified with that. That is what we have been using again. So if the product space is regular, the subspace will be regular. That means each factor is regular. That is easy. We shall now prove the converse. Pick up x belonging to U, where U is open in xj. Okay. So we must produce another subset, open subset, such that its closure is contained inside U, and this open subset contains x. So between x and U, I must squeeze another open set. Okay. So in the product topology, something is open means it's a neighborhood of this means there is a basic open set, and basic open set look like what? We have a finite subset I of j and open subsets vi contained inside xi such that the ith coordinate is inside vi for all I inside I. This I is a finite set, and look at pi inverse of all this I ring from 1 to n, it's like that, finite product, I inside a capital I, vi's. That obviously contains x, okay, and that will be contained inside U. This is a basic open set. All basic open sets look like this. So actually regularity can be checked by just using basic open sets. If I show that inside it I can get another, say W, such that W bar is contained inside this one, then the same thing as doing it for U. Okay. So I have come to assuming all the, you could have assumed that U itself is basic open set. That's all. Now for each xi being regular, for each x little I contained inside vi's are open, you can find an open subset wi in xi such that xi is inside wi, inside wi bar, inside vi. Between x little I and v little I, we can squeeze another open set Wi. So this I can do for all I inside I, and then I take product of these finite limited Wi's. That I am calling it as W. Then one thing which we have already checked all the time is the closure of this product is the product of the closures. Each closure here is containing corresponding VI, so this product will be containing the product of VIs. Okay. Now if you take P inverse, Pi inverse of this one, X will be inside Pi inverse of W, which because each the ith coordinate X capital I is inside W by the very choice. Xi's are inside W. So X is inside Pi inverse of W. Automatically this will be contained in this closure. What I need to show it is contained inside U, right? Now this is a closed subset containing this one, and this is also a closed subset. Pi is an open map. It is actually a continuous map. So Pi inverse of closed subset is closed, and it contains Pi inverse of W. Therefore, this closure is contained inside this one. Actually, these are equal here, but I am just taking the easy way. This is contained inside this. That's no doubt. And this has been chosen such that this inside U, because what is this Pi inverse of W bar? See, W bar is inside this one. So Pi inverse of W bar is Pi inverse of these, and these things are contained inside U. That is a choice of VIs. So that completes the proof. So not much hard work here. Regularity is productive. So in that sense, it is nearer to Hausdorffness, right? Indeed, there is two schools of thought in topology. One, people use Hausdorffness whenever they have difficulty. The other school uses regularity whenever they have difficulty. And they achieve similar results. In fact, identical results. Okay. So in that sense, regularity is quite nearer, but in a slightly different way they work. Nearer to Hausdorffness is what I wanted to say. Okay. But somewhat surprisingly, normality, which we tend to think like nearer to regularity, it has weird properties. Normality is not even finite productive. The reason may be because it is not even hereditary. Okay, even one way is, even if X cross Y is normal, it doesn't imply that X is normal and Y is normal. That is a funny thing here. So we shall see now such an example. The example that we are going to see is one of the beautiful examples which you are already familiar with, and we have studied quite a few properties of that. That is the semi-open interval topology. X is the real line with the semi-interval topology. Namely, the base consists of half closed intervals, A closed, B open. Okay, very specific, because that is why it's called L, semi-interval. You could have write it as R also. That would be A open and B closed. So that is somewhat due to that. These two are homeomorphic to each other. So if you study one of them, the other one is same. By just writing X goes to minus X, you will get the other topology. So that will be X going to minus X will be homeomorphism. Okay, so concentrate on the semi-interval topology. Each open interval can be written as a union of semi-open intervals of this form, right? Suppose you want to write open A comma B, then all that I have to do is closed A plus 1 by n, okay, comma B, union over all n will be equal to open AB, right? So all open intervals are also can be written as this one. It follows that this thing is finer than the usual topology, because all the open subsets in the usual topology will be also open in this topology. However, this closed interval and half closed intervals are not open in the usual topology. So this is finer, strictly finer than the usual topology. Anything finer than a Hausdorff space will be also Hausdorff. Therefore, this space is Hausdorff. Okay. Now observe that every semi-open interval is also closed in L. Okay. So when you have a base consisting of closed sets, it must be base-hole topology, therefore they are open also, open and closed. Okay, that itself is a very strong property, and people have studied such things. So whatever you study those, this example will completely fit into that. Okay. So all those properties will be there for this RL. Okay. Closed intervals are closed inside a usual topology, but here even half closed intervals, okay, they are both open as well as closed in this topology. Why is this closed? Because what is complement? B to infinity, so that is by definition is an open set. Minus infinity to A open, that is also an open subset, because you have just seen that every open subset in R is also open here. Okay. So you can take X belonging to such a basic open set AB, that is an open set. Then you can choose AB itself as the subspace also. Its closure will be itself. So regularity is satisfied vacuously here. You don't have to choose another W at all. You have already seen that this space is Lindelof and the product is not Lindelof. You remember that? This was as a remark. Let me just show you that we have already done this one by taking the product and showing that the diagonal is discrete. Remember that this was the example, right? So here we had shown that the product is not Lindelof. Therefore, you can deduce a lot of things, namely, of course, this itself is Lindelof, we have seen. So this was not all that trivial. Okay, you have to use the second countability of the usual topology and so on. Okay, so but I don't have to repeat that. Okay, we have seen this one, that the space is Lindelof, but the product is not Lindelof. All right. Now, I want to tell you that this semi-interval topology is not second countable. You see, second countable would be imply Lindelof, but this is an example of Lindelof space which is not second countable. Why? If it were second countable, the product will be also second countable, because second countability is finite product invariant. Okay, finite productive. That also you have seen. But once X cross X is second countable, it will be Lindelof also. So that will contradict the previous observation that we have done. All right. So this is a space which is Lindelof but not second countable. Okay. Now here is a remark. We have used finite product invariance of second countability in a peculiar way to see that it is not second countable. Okay, a space is not second countable. So you see, you can use certain theorems in a negative way also. So they also help in this way. All right. Now let us continue with this space. Finally, I want to show that the product is not normal. Okay, non-normality of the product space. Just now we showed that this is a regular space, right? And the product is a product of two regular space regular. So you will get there is a regular space, but not normal. Okay. So how do you show that this semi-integral topology product with itself is not normal? Once again, we go back and see that the diagonal is a closed subspace, all right. Okay, in the product, it is actually discrete. So that is what we had seen before. Okay, but now we want to use it very crucially, all right. So we have seen above that the induced topology on delta twiddle, usually delta will denote the diagonal x comma x. So this is x comma minus x. This is discrete. Okay. Why? Because you could take a half open interval cross half open interval, just touching the point on the diagonal. The stuff it is contained inside the one side of the whole diagonal. So if that is an open set, intersects with the diagonal will be a single point. So that single point is open. That is how we have done it. Now, this will help us in showing that the product is not normal. We take A to be the set of all points x comma minus x, with x being rational. Okay. Any subset is closed now. Okay. Similarly, you take B to be the complement of A, that will be also closed. If it's closed, because it's a discrete set, it's closed inside the delta twiddle. Delta twiddle is closed in the whole space. So these two are now disjoint closed subsets of X. Okay. R comma minus R, where R is rational. Other one is R comma minus R, where R is irrational. Now we claim that there exists no open sets U and V containing A and B respectively, such that their intersection is empty. In other words, we start with U and V open, A contained inside U, B contained inside V, then we show that U intersection V is not empty. Assuming on the contrary, that means what? Suppose you have two open subsets A and B, containing A and B respectively, U and V. Once they are open, it follows that for each X inside R, okay, there exists a positive real number epsilon X, such that X comma X plus epsilon X open cross another one minus X comma minus X cross epsilon X, this open. See, these are points of our RL, and this is the product topology, right? So I'm taking a product neighborhood, which is the basic neighborhood in the product topology. This is contained inside U or contained inside V according as X is rational or irrational. If X is rational, it will be inside U. If X is irrational, it will be inside V. Okay. Of course, this length of this interval, x to x plus epsilon x, this epsilon x will depend upon x. All right. So now fix a rational number S not belonging to Q. It follows that for all irrational numbers T belonging to S naught minus epsilon S naught. What is this epsilon? We have fixed these epsilon x's, remember that. So I'm taking the same thing here. S naught minus epsilon S naught, comma S naught. The y coordinate of S naught is this one, but the x coordinate is slightly smaller. Okay, actually I should take this one to be minus S naught, okay, because I am interested in the points on that anti-diagonal. Okay, irrational numbers T, okay, belonging to this open set. This part is okay. This is just S naught here. We have epsilon T, the corresponding epsilon T must be less than epsilon S naught by 2. Okay, it follows that for irrational numbers, we have epsilon T less than or equal to S naught minus T. Because otherwise it will collide with it will go inside V. So this is irrational number. So this epsilon T is less than S naught minus T. Okay. Because I have taken T to be inside this one, namely slightly smaller than S naught, but inside this interval. Okay, the corresponding epsilon T cannot exceed that one. Okay, U and V are disjoint is used here. Okay, so that's why this must be less than epsilon. Now, inside this one, now choose an irrational number T naught such that S naught minus T naught is less than epsilon S naught by 2. See, so I am further cut it down. You can choose another irrational number here. Okay, the irrational number will also have same property. Okay, in particular, we have epsilon of T naught will be less than epsilon of S naught by 2. That is all I am using. Now you interchange the role of the irrational number and rational number. You started with S naught, you got a T naught with all this property. You fix this one. Now apply the same argument to T naught to get a rational number with the same property, but this time you write it as S1. Repeat the above argument. Okay, with T naught in place of S naught to obtain a rational number S1 in the interval T naught comma T naught plus epsilon T naught such that epsilon of S1 is less than or epsilon of T naught by 2, which is epsilon of S naught divided by 2 square. Okay, so this is a consequence of epsilon T naught itself is less than epsilon S naught by 2. So one stage of construction is over. Starting with a rational number, you get an irrational number with some property, closer, that's all. And then irrational number, you get again a rational number. One cycle is over. Now repeat this cycle. Repeat it. So what you get? You get a sequence. Okay, so I will show you first. I'll show you what in the first stage what happens. Starting with a rational number here, it has some epsilon S naught here, epsilon S naught here. Okay, and T naught is just little smaller, on this side. Corresponding length of this one, it should not come over here. You see, otherwise these two will not be disjoint. So it has to be at the most this much, right? So this epsilon T naught will have to be smaller than the difference between S naught and T naught. So that's all I have put. Okay. Yeah. Whether I choose it here or here, it is the same thing. All right. But I have meticulously chosen it behind here. That's all. Okay. Now I can choose the T naught, the next rational on this side. So S naught, T naught, S1, T1, S2, T2, just like in in the proof of Leibniz series. Okay. Alternatively, they will be between T0 and T0 and S0. Okay, so that's how I'm going to choose those numbers here. That is, for one cycle is clearly stated and you repeat it. Okay, so what do you get? Repeating this process, we get two sequences, Sn and Tn, such that each Sn is rational number, each Tn is an irrational number. Tn's are inside Sn minus epsilon Sn by 2, comma Sn, and Sn plus 1s are inside Tn, comma Tn plus epsilon Tn by 2. So this minus, this is on the left side, this is on the plus side, on this side, for all n. Okay, and epsilon Tn will be less than or equal to epsilon Sn by 2, and that is less than or equal to epsilon Tn minus 1 by 2 square, and so on. Also on epsilon S naught divided by 2 to the 2 power n you get, 2 to the 2n you get. When you, by the nth stage, you will have what? 2 square, 2 to the 4, and so on, 2 to the 2n for all n. For all irrational numbers t between Sn and Sn by 2, comma Sn, we have epsilon t is less than or equal to epsilon Sn by 2. Once you have chosen that one, for everything in between also, the length of those intervals which you have chosen has to be short, otherwise they will collide with the other one which you have chosen for the rational numbers. Okay, the basic assumption is that u and v are disjoint. Therefore, it's you get. All right. So that is all. Now you see that there is a contradiction here. For all rational numbers, for the same reason, S belonging to Tn plus epsilon Tn by 2, we should have epsilon S less than this number. So it follows that both the sequences tend to a common limit. Okay, say R. This clearly Sn is decreasing and Tn is increasing. I told you this is similar to the proof of alternating series. Why it is convergent? It is similar to that. Sn is decreasing and Tn is increasing monotonically, and hence the limit will be between Tn and Sn. Tn is less than or equal to R, less than or equal to Sn for all n. But then from 6 and 7 combined together, whether R is irrational or rational, it follows that the corresponding epsilon R has to be less than epsilon S naught by 2 power 2n. So everything in between, see, it has to satisfy this one. Because if it's a rational number, it will work. Irrational number, the other one will work. Okay. So these are two statements here. Therefore, what we have is, this is true for all n. This R is independent of n. So when you take the limit of this, it will show that epsilon R is 0. So contradiction is to the fact that we can choose, open rectangles around each point on the diagonal, such that one set of rectangles are inside U, other are inside V, they are disjoint. So one small observation is that this semi-interval topology is not metrizable. Why? Because if it's metrizable, its product will be also metrizable. Metrizable means what? There is a metric. The product topology is given by the product metric, right? If it's product metric, then it will be normal also. That's an absurd thing, because just now we proved that it is not normal. Okay, so that's a contradiction. Just the way we have just defined that, it was not at all clear that such a thing happens. Okay, here I have put a few exercises to you. Try them. They will only illustrate and more about this familiarity. You will get familiarity with the concepts here. A complete regular is hereditary. Okay, so hereditariness goes Hausdorffness, then regularity, complete regularity. Normality, it will fail. That's what you must know. Topological space, S is a base for it. Complete regularity. Okay, you have to verify for all point X and an open subset. You don't have to. You have to just verify it for only a sub-base. You have to prove that. Each point X belonging to X, V inside only the subspace, sub-base, X belonging to V, there exists a continuous function such that fx is 1 and f of the complement of V is 0. Enough to verify all these statements for basic open sets is easy. Sub-basic open sets, you have to just be careful and be done with it, and you can verify this here. So that will be helpful, especially while dealing with products. So I have put that one as a illustrative example, exercise, which will help you to solve the next exercise. Show that the product of completely regular spaces is completely regular. One way is obvious because of the hereditariness. Okay. After that, you show that the lower limit topology RL is completely regular, and hence conclude that RL cross RL is completely regular. Okay. In particular, this gives you an example of a completely regular space which is not normal. We just prove that it is not normal. Okay. So let us stop here and take up this study next time. Thank you.